This is the title of my presentation, Basics of River Osmosis and Nanofiltration. This is my name, Juan Antonio López Ramírez. I'm full professor at the Department of Environmental Technology in the Faculty of Sea Science and Sea and Environmental Sciences at the University of Cadiz, Spain. Okay, so let's talk about desalination. Why desalination? Why we need desalination in Spain? Okay, we are about 48 million people around, but we are suffering from time to time droughts of periods of drought, very strong. So now we are facing a very strong drought, about more than 2 years and a half, almost no rain. Just the 15 days ago, it was raining heavily, very heavily in Spain, but our dams are still empty. Just a few of them are full, but only the smallest one. The biggest are still empty of water, and summer is coming. Think that in Spain, we are about 48 million people, but we receive around the year more than 80 million people. So that means that it's about the consumption of for a country of more than 120 million. Okay. So and also the same are two non-conventional resources that are extremely used in Spain. Okay. Right now, Spain is about the sixth power in the world using desalination. So let's talk something about desalination plants just for the introduction. You can see here a picture, and this is for a huge plant for seawater, but we can find many different sizes for desalination plants. Here, this is another industrial desalination plant. This is about 20,000 cubic meters a day production for seawater. So you need great devices for the production of water, great pumps, very powerful pumps, a lot of filters, and a lot of membranes. Here you can see one of our big desalination plants in the Mediterranean Sea. Maybe you can see with the mouse here the filters for the pretreatment, and these are the core of the plant where the membranes are. Okay, but also we can find very small devices like this, for instance, that you can put in a container and send in a truck to any place, or even for just domestic uses. So desalination, or river osmosis and nanofiltration are very powerful technologies because are very easy to scale up. Okay, from the very small systems to the very big and huge systems. So it's a very interesting technology in this case. Okay, how is the diagram? How complex is one seawater desalination plant? Okay, here we take the water. This is the intake from the water. It can be in the well on the coast, or you can see an open intake. It depends. But usually we have sand filters, cartridge filters, some kind of chemicals addition, maybe coagulants, sodium hypochlorite to kill microorganisms, and finally the high pressure pump and the membrane. And finally, water is so good that cannot be drunk directly, so we need to make some kind of post-treatment to re-equilibrate the salt content. And finally, you can pump the water to the users. Users then in Spain can be the cities, the people, but also the crops. There are some huge desalination plants in Spain just for irrigation. And the farmers pay the cost of the treatment. Okay. So let's start from the very beginning. River osmosis and nanofiltration are membrane technologies. what are membrane technologies? Well, this kind of technology is based on the use of semi-permeable membranes that allow passage of solvent through the porous medium. Sometimes it's porous, sometimes it's non-porous, okay? Like reverse osmosis and nanofiltration, they are non-porous. And the water can pass through the membrane, but other components of the water, I mean particles, solutes, salts, ions, organic molecules, and microorganisms, are retained according to their size. The membrane usually has a thickness between 0.05 millimeters and 2 millimeters, depending on the nature of the membrane, and it acts like a selective barrier. So allows the pass of certain components and retain another ones. Okay. So let's take a very short overview about the history. The first desalination plants in this planet were produced by the Phoenicians. The Phoenicians traveled from the Eastern Mediterranean to the Western Mediterranean, and they put some spongy on the ships. They put on fire some boiling water, and they put spongy with a net, and they recover the steam. Later, the sailors took those spongy full of water, of steam of water, and they push up and they obtain water. So that were the first desalination plants that we know. Or of course, well, plants is not probably the best word. Okay, but well, in 1953 at University of Florida in USA, they produced the first membrane. Okay, probably the first current membrane. Okay, so it was made with it had a very low flow, but a nice salt rejection. Later in 1960, the cellulose acetate membranes, that was the first commercial membranes, was created. And you can see that in just a few years, the first water supply using reverse osmosis was created, just in 1965, just 5 years after the first modern membrane. Okay. So in the 70s, the first industrial plants were producing water. And now we have many different demands of water in the industry, just to conserve water, to reduce energy, new application, strong legislation. And so this kind of desalination technologies, reverse osmosis and nanofiltration, are more and more attractive. So they are currently very widely used in the industry. And the water industry will need bigger desalination plants in the next few years. And now the market in the, you can see that the membrane technology market in the world is very, very important, about $6.6 billion US the last years. And, oh, sorry, there is something wrong. I mean, it will be about more than $12 billion in 2028. Okay. So, and this is something important. Usually, in membrane desalination, we want to obtain water. Sometimes water is not our goal. Sometimes we need to recover salts. For instance, in some nuclear power plants, we need to recover radionuclides or contamination, or in the milky industry, we need to retain proteins, vitamins, I mean the solute, but not the water. It depends. So desalination using reverse osmosis and nanofiltration is a separator concentrator process. So you can obtain the water without salts, or you can obtain the concentrate. So it depends. In this lesson presentation, the main objective will be to obtain water. Okay. So membranes are employed to remove colloidal and dissolved solids in the water. And these kind of technologies are preferred to be used more than another kind of filtration processes. Why? Because these membranes have different and important characteristics. Current membranes have high permeability, so very nice production, high rejection for salts, very efficiently salt separation. These membranes have high flow, competitive prices, but they need well-designed pretreatment. This is a critical point, a key issue, the pretreatment, in order to avoid the fouling. Fouling probably is the main handicap in desalination or membrane technology, okay? The fouling. Fouling is when some components that are in the feed water are putting onto the surface of the membrane, fouling the surface, okay? We will pay attention to this issue later in my presentation. So the membrane is a barrier that separates two phases, usually water, okay, but sometimes we can use separate steam from water. It depends on the application, okay? And as I have said before, we can get the separation of one or more component in a liquid mixture or even in a gaseous mixture, okay? Applying some kind of driving forces, usually pressure, but not only pressure, okay? Maybe electric fields or maybe difference in concentrations, okay? In membrane technology, the mixture is forced to pass through the membrane, and we can achieve the separation based primarily on the size of the molecules present in the mixture. But sometimes in reverse osmosis and nanofiltration, this is not the truth. Sometimes even compounds or elements, even smaller than water, are well separated from the water. Okay, it's not just size. Right? It's very easy to understand that size is the main reason why the components can be separated from the feed water, but it's not really. The size is important, but it's not totally true. Okay, there are another topics that must be considered. Okay, which are the leading membrane technologies? Microfiltration, ultrafiltration, nanofiltration, reverse osmosis, electrodialysis, dialysis, gas separation, and membrane distillation. My expertise is in microfiltration, ultrafiltration, nanofiltration, reverse osmosis, and membrane distillation. These four I have used for treating brackish water and also seawater. But in the case of membrane distillation, I have applied this technology for the treatment of seawater, but also hazardous waste. And really, it works really, really nice. Okay. So here we have a nice slide, the filtration spectrum. And here you can see many different scales in the top. You can see visible to naked eye, optical microscope, or a different range from macroparticles, microparticles, macromolecular, molecular range, and ionic range, or in Armstrong, or even in molecular weight, okay? And here you can see different process for the separation. And here you have many different contaminants. Okay, so you need to remove, Giardia yeast in order to make potable water. Maybe you can use particle filtration. Conventional filtration, sand filtration. It's good, okay? So for some kind of bacteria, it also works. But for the smallest bacteria, particle filtration or sand filtration is unuseful. so you cannot obtain a safe water. You need to go to a stronger technology. So in this case, microfiltration can remove very efficiently bacteria, paint pigments, or different kind of contaminants. However, if we need to remove proteins, microfiltration is totally unuseful. We need stronger technology. Which one? Ultrafiltration. So we can remove very efficiently proteins, some kind of pyrogens, viruses, okay, very small particles, colloidal particles. But if we need to remove smaller components, I mean like carbohydrates, dyes, pesticides, herbicides, you cannot use ultrafiltration because it doesn't work. So we need to use nanofiltration. But in the case that we need to remove elements like chloride, I mean ions, okay? Anions like chloride, sulfates, or sodium, or calcium, we need to use reverse osmosis and sometimes nanofiltration, okay? Of course, if nanofiltration is able to remove pesticide from the water, it's also able to remove proteins, bacteria, Giardia keys, etc. Okay, so this is a very interesting slide, so you can compare different sizes and also different contaminants and also the most appropriate technology for it. Okay. Okay, so here you can see a nice picture. So the biggest particles can be very efficiently removed by microfiltration, but proteins and water can pass through the membrane. In the case of the ultrafiltration, these proteins can be well rejected, but smaller particles, smaller molecules like sugars cannot be removed. Nanofiltration can remove very efficiently organic molecules of very small size, but not all the salts. However, reverse osmosis can remove almost all the salts in the feed water. Okay. So something very important when we are treating with desalination, not so important in nanofiltration, but also important, is the phenomenon of natural osmosis. If we can see this picture at the left, here we have two chambers containing water. This is fresh water, and this is salty water. And if we put inside in the middle one membrane, okay, one reverse osmosis membrane, the fresh water is going to pass through the membrane, okay, and is going to dilute this salty water. When you obtain at the end of this phenomenon, at both sides of the membrane, you have same salt concentration. Okay, this is natural osmosis. This happens when you stay a lot of time taking a bath, for instance, in the sea or in the river, and you can see that your skin is rugged. Okay, so this is phenomenon, natural phenomenon. It's happening in our cells, in all our cells. Okay. Well, here you can see that fresh water enters in this chamber, and there is a different height at both sides. Okay, so this is higher than this. Okay, this difference of height, it is called osmotic pressure. This difference of pressure in this chamber, and this is the osmotic pressure. Okay, it depends on the salt content. Okay, so this is the natural phenomenon. What is reverse osmosis? Okay, let's imagine that we have a solution and it is in equilibrium. Okay, same salt concentration here, same salt concentration here. Okay, if we apply pressure in this size, in this side, okay, we apply pressure here. Water is going to pass through the membrane okay? But salts cannot pass through the membrane. They are retained, okay? So this will be more concentrated in salts, and this will be diluted, okay? So at the beginning, same salt concentration. At the end of the process, we have salty concentration, very, and here we have fresh water, okay? But we need to apply pressure, okay? This is reverse osmosis, okay? This is natural process. This is not a natural process. This is technological process, okay?
I suppose we have some problem in the connection of Professor Juan López.
Carry on. Thank you so much. Sorry, probably it was a disconnection, an internet connection. Okay, thank you.
Okay, you're welcome. Okay, so 1,000 milligrams per liter is about 0.8 bars, okay? Our tap water in Cadiz is about 500 ppms of for those parts of the world containing about 35,000 milligrams per liter of TDS, osmotic pressure is almost 27.5 bars, okay? And this is important to know. So some definitions. We will come back to the osmotic pressure in just a couple of slides. Feed water. The feed water, some definition important in reverse osmosis and nanofiltration. The feed water is the water entering in the reverse osmosis system, the desalination system, after pretreatment. Okay, it's the water that we need to treat. The product or the permeate is the water obtained through the membrane, the water that can pass through the membrane. The concentrate is the water that is rejected, okay, containing the most of the salts separated by the membranes. The recovery is the system efficiency, okay, it's the percentage of the feed water that becomes product, okay? So when we have a system that is working at 75% of recovery, that means that we are treating 100 cubic meters a day, we are producing 75 cubic meters of production, okay? That's the recovery. How much water we are obtaining from the feed water as a product. And the net applied pressure is the difference between the pressure that we are applying minus osmotic pressure, okay? Okay, let's see this slide that is very interesting. This only happens in permeable membranes, okay? When you have a membrane, you have a solution, and you are applying a force, and that makes the water pass through the membrane, the components are retained onto the membrane. That means that these components are more and more concentrated onto the membrane. So in the bulk solution, I mean in the middle of the pipe, the concentration has a value, but onto the membrane, the concentration is much higher, okay? So this is important that must be understood. So you can see here, the bulk concentration have a value, but as we are going closer to the membrane, the salt concentration increases, okay? You can see. And these two equations are very important. The water flux, okay, it's related with a constant, the permeability of the membrane, okay, and the difference between the pressure applied minus osmotic pressure, okay? Higher the pressure applied by the pump, okay, higher the water flux. And the salt flux, I mean the amount of salt that can pass through the membrane, okay, is related with the constant what? About the recovery. The question is permit flow ratio, feed water flow in percentage, okay? So when a desalination plant is working at 50% recovery, this is important to understand that the TDS in the concentrate is twice the initial concentration, okay? So imagine this is my membrane, okay? I'm putting the feed water, imagine 100 cubic meters a day. It's not easy to draw with the mouse, but I'm trying my best. This is the product. This is maybe some salts, the less soluble salts, can precipitate onto the membrane, okay? And that's important. So you cannot increase the recovery all you want. It depends of the water quality. For instance, for seawater, it's not possible to increase beyond 50% recovery because some salts can precipitate and the energy that you need to apply and the resistance of the membranes can be overcome. So it's not a good idea in seawater to 1% recovery. However, for brackish water, you can increase the recovery, but depending of the sparingly soluble salts, okay? So the salt transport in the membranes depends of the difference of salts, the permeability coefficient, the area, and the thickness of the membrane, okay? At constant temperature, the salt passage in the membrane will depend on the difference of concentration, okay? But not of the applied pressure. This is important, okay? Okay, so let's talk something about the flux. The flux is the rate of the permeate that is transported per unit of membrane area. Is this equation? This is a parameter that is very used in the design of a desalination system. GDF, gallons, square foot and day, okay? The GDF is an acronym. Is the ratio between the flow and the area, okay? You can use gallon square foot day or liter square meter hour. In Spain, of course, we use this. North Americans use gallon square foot day, okay? So, for instance, for one desalination system like this, I'm not going to enter in to explain everything, but this is important. here you have an example. You have a system that is treating 208 cubic meters hour. In the first stage, we have 40 pressure vessels. In the second stage, we have 20 pressure vessels in a relation of 2:1. 6 membrane elements per pressure vessel. Now we will see what is everything. Okay, and containing this kind of membranes. Okay, let's see. Yeah. Okay. Finally, you can obtain the 9.1 GFD. Okay, so this parameter is important because it's saying to you if your system is conservative or it's not conservative, depending of the water quality. Okay, if you need to treat very nice water, okay, just containing some salts, almost no sapendosolids, very few bacteria, very few colloid concentration, you can increase very much the recovery. However, if you are treating with dirty water, okay, containing a lot of sapendosolids, a lot of salts, you need to reduce the GFD, your flux. Okay, so flux is very related with the water quality. The higher tendency of the water to fold the membrane, the lower GFD that you need to use in your system. Okay, and the lower tendency of the water to fold the membrane, the higher flux you can use. Okay. So a typical desalination plant scheme is like this. We have the pressure pan, the high pressure pan. This is the typical desalination plant scheme. Of course, there are two relationships that must be accomplished. I mean, the conservation solvent, okay, the feed water flow is equal to the sum of the product and reaction, okay? And the solute you must accomplish with this, okay? So water and salts have to go anywhere, okay? Okay, let's talk about the membrane. The membrane is the heart of the system, okay? Of course, you already know it's a semi-permeable barrier. And this membrane is usually a thin layer, okay, that cannot, alone, it cannot bear the stress during the separation process because we are applying pressure, sometimes very high pressure. So it is integrated in a structure that gives rigidity and optimizes the volume. And we have different types of classification. We have symmetrical membranes and also asymmetrical membranes. For microfiltration and ultrafiltration, depending, but we can find symmetrical membranes. That means that the top and the down of the membrane have same configuration. But in the case of desalination, we have asymmetrical membranes. It's the industrial, the standard in the industry. Okay, we have asymmetrical membrane. This is an example. In this case, you can see a micrograph of the porous asymmetric ultrafiltration membrane. You can see that if we cut in this plane, this has a different configuration of this. This is the skin of the membrane. This is the place where the components of the solution can be rejected. I mean, proteins, bacteria cannot pass through this part, okay? But water and the smallest component can pass through the membrane easily. And so once they enter in the membrane, they escape very easily. Okay, so here the permit is running to get out of the membrane. Okay, but here is where the separation. Okay, let's the components are rejected. Okay. So maybe you are asking, because I said before at the beginning, we have porous and non-porous membranes. Okay. Nanofiltration and reverse osmosis use non-porous membranes. What does it mean? Okay, that means that when somebody made the first classification, the technology at that moment could not distinguish any kind of porous intramembranes. Now with computers, we can figure out how the porous in the desalination membranes could be. Okay, this is a simulation. Really, we cannot see the porous. This is not really porous, it's just a intermolecular separation. Okay, but it's good enough that allow the passage of water. We can see. Okay, water. These are water molecules. This is the oxygen. Okay, this is the oxygen. This is the hydrogen. Okay, so water molecules are oriented into the space. They adopt the same position, and so they can pass through the membrane, thanks to the hydrogen bonds, hydrogen bridges between the membrane molecules and the water membrane configuration. Okay, so this is the secret why water can pass through in the membrane, but ions like sodium chloride cannot pass through the membrane. Okay, we will see in a few minutes a video and you will understand what's meaning. Okay. You have talked about the membrane. Let's talk about the pump. The pump is the heart of the plant. Okay, it consumes the most of the energy, especially in seawater. So proper selection is very important. And we have to pay attention to the performance, the investment, the maintenance, the noise, even the vibration, especially for the big ones. Okay. So in membrane desalination, we have two kinds: the positive displacement pumps and the centrifuge. Okay. The positive displacement pumps is like a piston. So this piston is pushing the water. Okay. So it has a motor and we have a piston. Okay, that is pushing the water to the system. Okay. You must be very careful in case some valve is closed. We can provoke an important accident and somebody can be injured. The problem with these pumps is that you can obtain it has an advantage and also a disadvantage. The advantage is that you can get very high pressure. Okay, very high pressure. However, you have pulsations. Okay? You have pulsations. So the pressure is not constant. It's vibrating. Okay, the pressure gauge is moving. Okay, so you need to use dampers. Sometimes they don't work properly. But well, for instance, this is my smallest desalination plant. Here we put the membrane in this small container, and this is my desalination plant. So I can work until 70 bars. Okay, and so we use small pieces of membranes, so we can make demonstration, or we can make a test for the membranes, for the selection of the best membranes, or for washing the membranes. Sometimes when the membranes are fouled by the components, you need to develop some washing protocols. So we use this very small plant, and well, we use this displacement pump and this small desalination system. Okay. The problem with this kind of pump, we need high maintenance. Okay. Here you can see the damper. Okay. For the biggest plants, usually centrifugal pumps are used. Okay. There are different kind of centrifugal pumps, the Siemens and the split case pumps, the more robust. Okay. So for bigger plants, centrifugal, no doubt. Okay. Absence of pulsations, more operational, lower maintenance. Okay. And when you need high flows, okay, more than 25, you need to use centrifugal pumps. For instance, this is one of 12 pumps like this that we have in one of our biggest desalination plants in Spain. It was the biggest in Europe until 2005, 2008 was the biggest desalination plant in the Mediterranean Sea, but now they are much bigger. You can see this is a person and this is the pump. So huge pump for huge plants. And there are 12 like this. In this plant, there are 12 like this. Huge pump. Okay, something very important. Desalination, especially for seawater, is an energy issue. More than 50% of the costs are related for the energy, okay, in the case of seawater. So energy recovery systems is a key issue for big plants because we can obtain a cost reduction during the facility operation. So it's very important to improve energy recovery system. So if you want to obtain the energy maximum efficiency, you will need to use this kind of energy recovery system and you will make or you will obtain the minimal cost in your facility. And this is a key factor, okay? So let's see what the industry has done along the history. Okay, sorry. Yeah, okay. So it's a little bit tricky now. Okay. Sorry. This is a multi-effect distillation plant. This is the distillation plant. You are burning fuel like oil, okay? You obtain heat and you distillate water, okay? So for this kind of system that are this sophisticated distillation processes, you need about 33 kilowatts hour of thermal energy to obtain 1 cubic meter, okay? First desalination, reverse osmosis membranes in the 70s needed about 35 kilowatts hour per cubic meter. But the membrane industry was producing better and more efficient membranes along the time. Nowadays, the huge reverse osmosis plants for seawater are about 3.5 kilowatts hour cubic meter. So one order of magnitude in just 30, 40 years, okay? So the energy consumption has reduced dramatically in the last year. And the minimum theoretical is the thermodynamical minimum theoretical is about 0.9 kilowatts hour cubic meter. Now the membrane industry is using nanotechnology applied to the membranes in order to reduce even more the consumption, okay? And to optimize the energy consumption in the plant. And also we need better performance in the pumps, okay, new kind of coating inside of the pipes, etc. So, sorry, this is in Spanish, but you will understand very easily. This is the oil price, the Brent oil price along the time, from the 70s, okay, to the beginning of 21st century. You can see that the cost of the energy has increased in an important way, okay? And the problem that you know that geopolitical issues have a very strong impact in the oil price. For instance, in 2010, the Brent was about $76. In 2011 was almost $124. With the fracking development in the US was 38. Today, the Brent is 71. I have a look, checking today, 71, something like that. Okay. So the energy, the cost of the oil is very volatile, depending on the geopolitical issues. So it's something that we must take in account. Okay. What happened with the membrane cost? In the 80s, the membranes were very expensive. Nowadays, you can find a stabilization in the cost per installed cubic meter. Okay, it's about. Now you can even buy in some big companies you can buy in the internet. The huge company, I'm not going to make any kind of advertising, but you can buy by internet membranes, and they deliver in your house for a small or domestic or for a small research. You can find them. Some years ago, it was almost impossible. Okay. So the energy recovery in reverse osmosis, the average consumption is about 4.5 kilowatts hour per cubic meter for a typical membrane. But if we are using recovery system, we can improve until 3.5. Okay, so it's it's a thing that in the case of the huge plant, you are treating more than 100,000 cubic meters a day, sometimes even 200,000 cubic meters a day. So to reduce 1.5 kilowatts hour per cubic meter is a lot of energy in one day. And these plants are working usually 24/7. I mean, all the whole day are working along the year. Okay. So 3.5 kilowatts hour cubic meter. It's too much energy, it's very few energy. Well, it's the equivalent to the electricity consumption of a heating system of an air conditioning for a family of 4 people during 1.5 hours, or traveling with a car almost 5 kilometers for a vehicle emitting 230 grams of CO2 per kilometer. So it's too much energy. It depends. I think I always say it depends on the need the need of water that you have. If you have an important need for water to produce water, you will pay all you need to in order to have water. Okay, to give water to your population. Okay, there are several kind of energy recovery system. Just you can see it, you can check in internet. For instance, this was the Pelton pump. This is the pressure, and you have the same axis. You use a turbine. This was the first system to reduce the energy consumption, but it's very inefficient. Was the first one, it's very inefficient. Now, sorry, this is a very efficient system. This is a ceramic system. It's a worldwide use, and you can check in the internet how they work. we don't have enough time to show, but here you can see that the most important that you have to take into account is that in the entrance of your desalination membrane, you are applying, in this case, 69 bars, okay? You obtain the permeate, and the reaction has a lot of pressure, about 67 bars. So you have a lot of energy in this water current, okay, in this water stream. So you put in this system, and from the seawater, you derive one part here. This is pushing away the low pressure brine, but here is entering high pressure, and you pressurize until 66 bars. So you transfer pressure from the concentrate to the feed part of the feed water, okay? Now you have 66 bars. Here in this item you had 76, 76. And now you put a small booster pan, and now you have 69, okay? This is from the seawater, you pressurize 69, and when you put the 3 bars of the booster pan to the 66, now this water can enter in this pipe, okay? So it's a way to reduce or to improve the energy recovery. Okay. Just a short idea about the pressure vessels. This is the place where you put your membranes. You can find different configuration for the for the smallest membranes and for the big ones, okay? Different diameters, different lengths, okay? The most important, they must be selected according to the pressure that you are going to work with. So if you are going to work with brackish water, usually with pressure vessel resisting 40 bars is enough. But if you are going to work with seawater and you can use until 70 bars, you need to use the stronger, the more resistance, okay? The most resistant. Well, the membrane, recording. These are porous membranes for microfiltration and microfiltration. You can see the pores, okay? But remember, nanofiltration and reverse osmosis have no pores, okay? According to the classification. Well, which are the polymers that are used for reverse osmosis and nanofiltration? Well, mainly they are made of organic polymers, okay, like cellulose acetate membranes or aromatic polyamide, okay. This is the structure of the aromatic polyamide at the top, and here down is the cellulose acetate. It's very easy. This slide is very interesting because you can see that this is almost flat. The molecule is almost flat, and this is not flat. And this is very important for the performance. Okay, these were old-fashioned membranes because they are not currently used, or they are not almost used. And the standard in the industry is aromatic polyamide membrane. And you can see that it has a peak and valley structure. Okay. So if we analyze atomic force microscopy, okay, this is the surface of the cellulose acetate membranes, and this is the aromatic polyamide membrane. Okay, you can see this is almost flat. Okay, and this is peak and valley. But please pay attention to the z-axis. Here you can see that there is a division. This is 20 nanometers. Okay, this is 20 nanometers. In this case, the division is 400 nanometers. Okay, not 20 like this. So this is almost flat, and this is compressed. Really, this will be we couldn't see in this slide because it will be very huge mountains. Okay, so this peak and valley structure, okay, is very important in the aromatic polyamide membrane. Why? For this reason. Okay? This is almost flat and this is peak and valley structure. Well, here with the cellulose acetate membranes, bacteria, colloids, etc., cannot find a place to hide. Okay, or it's not easy for them to put onto a membrane because they are swept out of the membrane by the water. Okay, for instance, this is a clean nanofiltration membrane, commercial nanofiltration membrane with a peak and valley structure. And here you can see that this is a fouled membrane. So this is full of colloids, molecules, organic molecules, and bacteria. So they find places to hide. They can put in these valleys. And so the water turbulence is not good enough to remove all these colloids, bacteria, particles. So these membranes are much more easy to foul than the cellulose acetate membrane. So for aromatic polyamide membranes, fouling is an important issue because they tend to get fouled very easily. They're also very sensitive to the oxidizers like sodium hypochlorite. Sodium hypochlorite is very commonly used to kill bacteria, and this hypochlorite oxidizes the membrane, so they are very sensitive to oxidants. And so maybe you are asking, okay, so it's very sensitive to the fouling, it's very sensitive to oxidants. Cellulose acetate membranes are not sensitive to fouling, or not so much, and they are more resistant to sodium hypochlorite than aromatic polyamide membrane. So which is the advantage? The advantage is that these aromatic polyamide membranes are much more productive at a lower pressure. And money is very, very important because the consumption, the kilowatts hour per cubic meter for aromatic polyamide membranes is much lower than in the case of cellulose acetate membrane. So this is the standard in the industry, aromatic polyamide membrane, despite of the fouling tendency. Okay. There are also in the market, you can find inorganic membranes, okay, even metallic membranes, okay. One here you can see this is a metallic membranes, okay. So inorganic membranes, they are ceramic made. They have a high structural and thermal resistance. They receive hypochlorite very well. But the problem is that they are very expensive. Okay, I have worked in a European project developing the first big nanofiltration honeycomb membrane, and they are working very well, but they are more expensive than aromatic polyamide membranes. Okay, so we have different configuration of membranes: the flat, the tubular, spiral, and the hollow fiber. Okay, let's see very quickly because I want to show you. I'm consuming almost my time, and so let's see. We have the flat membrane. You can see this is only for very special applications, for treating, for instance, leachates from the landfills. This is very polluted water. So this is only used for very dirty waters. Okay, it's not too much used. We also have the tubular configuration. They are also used for very dirty waters. For instance, in the agro-food industry, for treating fruit juices, for instance. And this is the standard in the industry. Okay, the spiral undet membrane. this has a configuration and a spiral, okay? And this is the standard. And also we can find, sorry, we are going to see a short video, and you will understand. This is the configuration. This is formed like a spiral here. You can see the boot, okay? And this has the hollow fiber. In Spain, there is only one big desalination plant using hollow fiber. It's about 150 kilometers far away from my university. And here you can see the hollow fiber. Okay, this is a scanning electron microscopy picture. And here you can see the video.
To create our standard spiral wound membranes, we construct the flat sheet membrane using Hydronautics automated casting equipment. We begin the process with a fabric support.
Can you listen the video?
Yes,
Yes,
Ah,
yes.
perfect. So
we can.
I'm going, perfect.
Yes, I'm listening. Yes.
So I'm going to rest my voice.
Base and then coat it with a microporous polysulfone layer. This provides additional support for the top 0.2 micron thick membrane barrier layer. This top barrier layer makes the actual separation to purify the water. The semi-permeable polyamide layer consists of a thin film of polymeric material a few thousand angstroms thick, formed on a porous supporting material. Semi-permeable membrane skin is formed on the polysulfone substrate by interfacial polymerization of monomers containing amine and carboxylic acid chloride functional groups. Hydronautics manufacturing procedure enables independent optimization of the distinct properties of the membrane.
Sorry, just a break. Here you can see this orange ball is maybe an element like sodium chloride, and it's surrounded by water. So the ions are removed or are rejected in the surface of the membrane because they are surrounded by water, but they cannot pass through because they don't have hydrogen bonds that can combine with the molecules of the membrane.
And salt-rejecting skin. The combination of these three layers makes a durable membrane flat sheet that is used in each spiral wound element. The membrane flat sheet is then combined with a sheet of feed channel spacer. This provides turbulence and creates space between the membrane sheets to allow uniform flow of the water to the entire membrane surface. The leads of membrane and feed channel spacer are then combined with a sheet of permeate spacer, which provides open flow channels for the permeate even under high pressure. The leaves are glued along each of the three exposed sides and then rolled around the core tube. With the back of the membrane completely sealed to the edges of the permeate spacer, the feed water is forced through the feed channel spacer, contacting the front or barrier layer of the membrane. Clean water, or permeate, passes through the membrane surface into the permeate channel and then flows in a spiral direction to the center of the element and is collected into the core tube. Hydronautics spiral wound elements can then be loaded into pressure vessels and interconnected with additional elements to complete any number of design specifications. Once the end adapter is connected to the last element and the pressure vessel is sealed, feed water can be introduced and then treated. The feed water that does not permeate through the membrane becomes enriched in salts as it travels through the feed channel spacer due to permeate water being removed. Typically, 8 to 10% of the water is removed in one 40-inch long membrane hub. It flows out the end of the vessel and is collected as the product. And the reject or concentrate from that vessel may then flow through another vessel, producing more permeate. The remaining concentrate may then be disposed of as waste or partially recycled as the feed. Typically, 70 to 90% of the water can be recovered as pure product water.
Okay. So, well, this is the influence of certain factors on membrane For instance, the permeate flux increases with the pressure in a linear way, and the salt reaction also increases with the pressure, but in an asymptotic curve. Respect the temperature, the permeate flux increases directly. Okay, it's about 3% per centigrade. Okay, per grade centigrade, and the salt reaction diminishes due to the lower viscosity. Okay. So the concentration polarization is also an important issue due to I consuming almost the time. Remember, I will show you that the concentration polarization is very important. Why? Because when water is passing through the membrane, the solutes, the salts, bacteria, are concentrating in this side of the membrane. So one increase in the concentration polarization means that there is a decrease in the product stream due to the increase of osmotic pressure in this side. Okay, remember, the flux depends on the pressure minus the pressure that your pump is producing minus osmotic pressure. Here, there is a value of concentration, of salt concentration, and also there is osmotic pressure. But when the concentration of salts is increasing close to the membrane, also the osmotic pressure increases. So the flux is lower than expected if the concentration polarization increases. Okay. Also, something happens, or something similar happens with the salt passage. Due that the salt passage depends on the difference of concentrations at both sides of the membranes, is not the same that we have this concentration like this one. So the higher the concentration here, the higher salt passage in this side of the membrane. Okay. And also, if this concentration polarization is very high, maybe there is precipitation of salts onto the membrane, reducing the flux, okay, and increasing the fouling. Well, so be very careful with the saturation limits of some salts in your solution that must be treated. Special caution with calcium sulfate, strontium sulfate, barium sulfate, and silica. These are very sparingly soluble salts, and you must pay attention to this salt, especially if you increase the saturation limits, because they are going to precipitate onto the membrane and they will reduce the flux. And when the flux is reduced, you need to use more and more energy to increase the pressure in order to maintain the flow rate production. Okay. Well, the fouling is very important in these systems because solutes can put or can deposit onto the membrane. What is going to happen with the fouling? Well, you can see when, for instance, with biofouling, the fouling is important because the colloids deposit into the membrane. But the problem with the biofouling is that bacteria are alive and they reproduce. And so one colloidal particle cannot reproduce, but one bacteria can reproduce very easily. So the problem with the effects of the biofouling must be taken in account. Why? Because there is a gradual decrease of flow and increase in differential pressure. So you need to use a higher pressure in your system. That means more energy, higher cost, and also there is a decrease in salt rejection. Okay, and now you can see in this slide the bacteria onto the membrane. Okay, these are bacteria, and you can see how they reproduce onto the membrane. Okay, And finally, I'm going to finish with an example of using membrane or desalination plants. In this case, was the ITAPERM project. I was the main researcher, and Professor Rafael Jiménez Castañeda was helping me, was the responsible for the energy. And we designed a plant that use only renewable energy. Okay, windmills. We had 2 windmills and a photovoltaic field, and the plant was experimental, so we controlled every variable in the process. We had a lot of sensors everywhere, and the main objective of this project was to increase the water quality, the drinking water quality in the Bay of Cadiz. In the Bay of Cadiz, about 400,000 people is drinking this water every day. Okay, so you can see the windmills. You can see the photovoltaic field, and this is all the energy control systems, okay, with the computer, electrical wardrobe, and these were the membrane, the pressure vessels and the membranes, okay, inside. And well, this is the daily energy production every day, and this was the consumption according to the pressure. We use nano filtrations because the amount of energy that you need for working is lower than reverse osmosis, and the water quality is almost same. So I decided to use nano filtration and not reverse osmosis. Okay. Well, you can see here the state of charge in red. You can see the state of charge of the battery during the night, because in this case we were using just only photovoltaic. During the night, the state of the charge was decreasing, and in the sunset we start to recharge the battery. You can see the photovoltaic production in a sunny day. Okay, and this is the consumption, the plant. Okay, and at the sunset, the battery is starting to give energy. Okay, so the type of energy, the percentage is decreasing. This is what is happening in a cloudy day. We are using more and more energy from the battery because the solar energy is not enough to maintain the system. In a windy day, you can see that the state of charge of the battery is totally full, because the energy, we had 2 windmills, 3 kilowatts each one, and in a windy day where they are continuously producing energy. Here they were disconnected by night, and so it was okay. And this is a breezy day. Usually we have very few breezy days along the year, so we need to use the energy stored in the battery. Okay. Well, we also made some simulations about the wind speed histogram in this location. Okay, depending of the wind speed, the energy, and the direction of blowing the wind. And in the ITAPERM project, we demonstrate that we can desalinate water without the use of conventional energy systems. We avoided the emission of 3 CO2 tons. That means that we avoided the emissions, or we made research. Our contribution was like 3 trees. Okay, and you can see here the CO2 emissions per country in Spain. Sorry, this is not 299. I have checked today. It's 246 grams CO2. We have a very important renewable energy contribution in Spain. Okay, Europe, Romania, Korea, and US. Okay, we also the tap water in our bay is nice, but we didn't know if the people would like the water of our project, and the 82% of the persons that taste the tap water and the desalinated water, they prefer our water to the metropolitan district water, the metropolitan water. Okay, the most of them prefer our water. Okay. Well, we did a lot of research. If somebody is interested, we have some papers and I can send. Okay. Here you can see, for instance, the calcium rejection. This is the concentration of calcium in feed water, and this is the permeate. You can see that the calcium concentration in the permeate was really, really low, despite of the increase with the drought period. With the drought period, the dam's water was worse. Okay? So you can see an increase in salts in our dams. And the conductivity you can see with the drought period was increased. Okay? And the conductivity in the permeate was really, really low. And trihalomethanes are very dangerous products that are produced during the chlorination in the drinking water plants. The conventional treatment produce this concentration of trihalomethanes, 30 micrograms per liter. We could reduce to 50% of the concentration. So the permeate was safer water than the conventional treatment that was based in the typical scheme of coagulation, flocculation, sedimentation, and filtration. Okay.